This is section 5.4, exponential models. In this lesson, we're going to model data with exponential functions, use percent change to determine if a data will fit an exponential model, and then compare linear, quadratic, and exponential models. All right, so let's talk about what data that's exponential will look like in a table of values. It has to do with percent change. So let's read through this first piece. It says if the percent change of outputs of a set of data is constant for equally spaced inputs, remember that's going to be a condition here. We want to make sure our x's or our inputs are equally spaced before we even determine anything. An exponential function will be a perfect fit for the data. So if we're looking at our outputs, our y's, and the percent change is constant, then we're going to say it's exponential. And to calculate the percent change, I'll show you that in 1 second here. If the percent change is approximately constant, then we say it's an approximate fit for the data. And if the percent change is not even approximately constant, then we would say an exponential function would not be appropriate for this data. So let's look at this set of data. You can see that our x's are equally spaced, 0, 1, 2, 3, 4, 5, so we can compare and look for this percent change. To calculate the percent change of the y's, you're going to calculate how much it grows by or changes by, so you can subtract the two values. This we can do in our head. 2 minus 1 gives me 1, divided by the first value that we started with, 1. So it grew by 1 and it started at 1. So 1 divided by 1 is equal to 1. If we're talking about a percent change, that's 100%. We take a decimal that's after the 1 and move it 2 spaces to the right. So let's look at the next set of data. Here I'm starting with 2. From 2 to 4, that's an increase of 2. I started with 2. 2 divided by 2 gives me 1. Let's look at the next set. I started with 4. 4 increased to 8. That's an increase of 4 divided by what I started with, 4, also gives me 1. And you'll notice whatever set I pick, let's say I pick 64, increase here from 64 to 128, if you subtract them, you get 64, divided by what you started with, will also give you 1, and that's going to be consistent throughout this table. So there is a constant percent change, a 100% change. So that means that an exponential model would be a good fit here. So if you want a quick little kind of, let's call it a formula that you could use, let's say you have two y values, any two y values in your table that are consecutive. You're going to do the second y value minus the first y value divided by the first y value, and that will calculate your percent change. Okay, so again, the one that comes second in the formula in the table minus the one that comes first in the table divided by the first one. Okay, but again, you're just calculating how much it's increasing by divided by what it started as, and that gives you your percent change. Okay, so let's look at these. We're going to compare first differences, which remember is where we just subtract, we find the difference, and percent change to determine if a linear function, so let's review, would be appropriate, or an exponential function would be appropriate. So let's look at A together. If I'm looking at A and I calculate my first difference, the difference between 6 and 2 is 4. The difference between 4 and 6, 14 and 6, is 8. 34 and 14, it's an increase of 20. And 81 and 34, that's an increase of 47. So you can see my first differences are not constant here, so a linear model would not be even close to appropriate. Now let's look at the percent changes. So we already have that difference, 6 minus 2, 14 minus 6, 34 minus 14. If I take those and divide by the first number, so divide this one by 2, divide this one by 6, divide by 14, divide by 34, we're going to get percentages. So 4 divided by 2 gives me 2. Turn that into a percent. It's 200%. 8 divided by 6 gives me 1.3 repeating, so that would be 133%. 20 divided by 14 gives me 1.43. So as a percentage, that would be 143%. And then 47 divided by 34 gives me 138%. It's 1.38 if I do that division. So you can see here, they're not constant for sure, but they're definitely a lot closer together in value, especially after that first one, than our first differences one was. So this would be more appropriate modeled with an exponential function. Still won't be a perfect exponential function, but it's a better model than our linear model. Okay, let's look at the next one. Let's look at those first differences. 1.1, if I subtract these, I get 1.2, 1.1, 1.1, 1.1. So you can see our first differences here are almost constant, almost exactly the same every time. So we can confidently say that a linear model would be more appropriate here. Now, if you want to check these, you can use your graphing calculator and look at a scatter plot and look at the shape of your data. So let me pull up my calculator here. I already went ahead and put this data in my L1 and L2. So let's look at our plot. You could do this in your calculator if you wanted to, but I just want to give you a quick picture of this. So I hit plot, zoom 9 is zoom stat, and you can see there is our data. This data isn't making a line, it's making that exponential curve shape that we talked about in the previous lesson. So that shape alone tells you that probably an exponential model is going to be appropriate. Now let's look at the one at the bottom. I actually put that data in another set of columns, so I'm going to use plot 2 to bring it up. And again, just zoom 9 to see the picture. And there is a picture of that second set of data from part B. So again, here the shape gives a lot away. Oop, I don't want to do that. Erase that. There we go. The shape gives a lot away here. You can see we're seeing a line in this data versus that curve in the data. So a curve tells you exponential, something that's increasing or decreasing constantly, making a line is more linear. Okay, so try these two on your own. Here again, we've got some tables of values. Instead of x and y, you've got x and some function notation, h of x. Test the percent change and determine if this is going to be exactly exponential, approximately exponential, or not exponential. So here you do not have to find the first differences, just the percent change, and then go from there. I'll give you a minute. All right, so let's take a look at those percent changes. So if I do 6 minus 2.5, I get 3.5 divided by 2.5, and I'll put that in my calculator in a second. 8.5 minus 6 is 2.5 over 6. 10 minus 8.5 is 1.5 over 8.5. 8 minus 10 gives me a negative 2 over 10. And 6 minus 8 gives me a negative 2 over 8. So probably because you're seeing those negatives, hopefully you kind of see the writing on the wall here. If I divide them, I get 1.4 or 140%. I get 0.42 or 42%. I get, let's see, about 18% for the next one. The next one I'm going to get 20%, negative 20% more accurately, and then negative 25%. So definitely not constant or even close to constant, so this would not be appropriate as an exponential model. And we'll look at the picture of that one in a second. Let's look at the next ones. Again, I'm going to subtract them. So essentially we're finding first differences here and then dividing. So 2.25 minus 1.5 gives me 0.75 over 1.5. 3.8 minus 2.25 is 1.55 divided by 2.25. 5 minus 3.8 gives me 1.2 over 3.8. 11 minus 5 gives me 6 over 5, and then 17 minus 11 gives me 6 over 11. Okay, and let's go ahead and divide those. I'm going to get for the first one 1/2, or 50% for my percent change. 1.55 divided by 2.25 gives me about 69%, 68.8. 1.2 divided by 3.8, I get 32%. 6 over 5 is going to give me, let's see here, 120%. And 6 over 11 is going to give me 55%. So not terrible here. I'm going to say right now it's approximately linear, but I'm going to double check my picture as well. Did I say linear? Approximately exponential. There we go. I have some percentages that are pretty close there, the 50, the 60, the 55, the 32. It's not terrible, but it's definitely not constant. Not ready to rule out exponential completely, though. All right, so let me show you the pictures of these, and we'll confirm with the scatter plot. So I went ahead and put all my data in here. You can see I've got it in L1 and L2 as my first set, and L3 and L4 as my second set. And I'm going to use my stat plots. You can just keep putting things in L1 and L2 if you don't want to get fancy with the calculator. So let's look at the first picture. Let me turn my plot 1 on, my plot 2 off, zoom 9. There's your first picture for part A. Now you can see that curve in the data. This can be modeled with, if you imagine drawing a parabola, a U-shape over this. A quadratic would be most appropriate for this data. So if you had a problem on your homework that asked would a linear or quadratic or exponential be more appropriate, a quadratic would be the most appropriate. Okay, and let's look at the second one. I'm going to turn my plot 1 off and my plot 2 on. Zoom 9, and then you can see here's my picture. So it's not great, but we are seeing that exponential curve shape happen here. So I would definitely say that approximately exponential would be the most appropriate answer for this. Okay, again, not perfect. If you ran an exponential model on this, which we'll do in a little bit, you wouldn't have a correlation coefficient that would be super strong, close to 1, but it'll be close. It'll be a decent model. So not exponential and approximately exponential are going to be our two answers here. Okay, so let's talk about writing models. We're going to focus right now on writing models by hand, and then I'll show you later how to do them in the calculator, like we've done with our other functions. So to write an exponential, we're going to be using this model, y equals a times b to the x power, which we've talked about before. A represents the initial value, okay? It's also going to be a y-intercept on the graph. B represents a growth rate, what you multiply by. So B is greater than 1 if it represents growth, and B is between 0 and 1 if it represents decay. Y represents a total amount, and X is your time periods. And then one more little note to make here, if you are increasing by a percentage, and your percentage is R, whatever that is, to calculate your B value, you're going to add R to 1, and R is a decimal. Let's remember that if we have a percentage, we're going to write it as a decimal. And if you're calculating decay, you're going to take it away from 1. So why are we doing that? That 1 represents the original 100%. If we want to increase by a percent, we add it on to 100%, and we get a value larger than 1 that makes it grow by that percentage for each unit of time. If we are decaying or decreasing, we're taking away from 100%, and that ensures that our formula is calculating not what we're losing, but what remains of the element or the item or the value of something that we're calculating. Okay, so make sure you have this written in your notes. A is starting amount, initial value, y-intercept, which is when x is 0. B is the growth rate. It's got to be bigger than 1 if it's growing, between 0 and 1 if it's decaying, and B is really what you're multiplying by from one term to the next, and we'll see that in a second. Y is a total amount, X time periods, and then there's a little hint to calculate the B if you're not sure if something's growing or decreasing by a percentage. Okay, so let's look at this one first. It says find the exponential function that models the table below. And let's say we're doing this without technology. Again, you'll see the technology part of it with our calculator in a little bit. So the first thing you want to look for is you want to look for an x value that's equal to 0. That x value that's equal to 0 represents your y-intercept, but more importantly for these, that's our a value. And you can see we have that in our table here. We have an x value of 0 and our y is 2. So we can confidently say that a is 2. The other value that you need to be able to write our exponential equation, and let me write that formula down again here for us, is your b value. To calculate your b value, if you have a table of values where your x's are increasing constantly from one term to the next, all you have to do is look at the y's and see what you're multiplying by. What you have to multiply by as the values of x increase are that growth rate. It tells us how the function is growing. So 2 times what gives me 6? It's 3. 6 times what gives me 18? It's 3. 18 times what gives me 54? It's 3. Or you could work backwards. 486 divided by 162 would equal 3. If you take any two values in your table and divide them, the later one by the earlier one, you're going to get that b value, and it's going to be constant throughout if it can be modeled with an exponential function. So we can say that the function for this table is y equals a, which is 2, our starting amount, initial value, y-intercept, b, what we're multiplying by from one term to the next, which is 3, and then we're going to take that to the x power. So now let's see what this looks like in a word problem. In this problem, the number of bacteria in a jar is 1,000. Every hour, the number of bacteria is expected to decrease by half. Write a function to model the number of bacteria after x hours. So again, let's talk about that first formula. Get that written down there, y equals a times b to the x. And now we want to think about what these values represent. A represents a starting amount. In this case, we're talking about bacteria. How many bacteria did we start with? We started with 1,000. B is our growth rate. Well, in this case, we're decreasing. So we want to make sure that our B value is a number that's smaller than 1. And if you're not sure what to use, think about what would you multiply by? After 1 hour, if I know that my bacteria is going to decrease by half, I would multiply by a half. I know there's going to be 500 after that first hour. So 1/2 is that B value. And then that's your answer. Nothing to calculate here, which is nice. Okay, let's try another one. The average price of a house in a certain city was $220,000 in 2008, and it increases at 3% per year. Write the equation of the exponential function that models the average price of the house t years after 2008. Okay, so again, let's write our formula down. We want to start with the initial value of the house. In this case, that's $220,000. B is our growth rate, and then the years here is represented with a t instead of an x, so we want to make sure we use that proper variable there. All right, we are increasing by 3% a year, so this is where we can use those little kind of helpful things we wrote down a few slides ago for B. If I want to calculate B and I'm increasing by a percentage, we're going to do 1 plus that percentage written as a decimal. Well, 3% written as a decimal is 0.03. So that tells me my B value is 1.03. It's 103% of the previous year's value if we're increasing by 3%. That's what that represents. And that's your answer for A. For part B, we want to use the model to predict the average price of the house in 2013. So all we have to do is figure out how many years since 2008 was that. And you can subtract them. That's 5 years difference. And then we're going to type this just in your calculator is fine. So 220,000 times 1.03 to the 5th power. And I'm going to round to the nearest penny here. $255,040, and it's 0.296. I'm going to say 0.30, 30 cents is the value of the home. Okay, let's look at one more of those. This one says at the end of an advertising campaign, weekly sales amounted to $20,000. They then decreased by 2% each week after the end of the campaign. Okay, and we want to make a note that that's a decreasing, so this is going to be a decay function. Write the equation of the exponential function that models the weekly sales. So again, let's start with y equals a times b to the x. My starting amount for that week was 20,000. And then each week after, it started to decrease by 2%. So here to calculate b, if you're decreasing by a percentage, you're going to do 1 minus your r value. So 1 minus 0.02 is going to give me 0.98, which means every week after, it's only worth 98% of what it was worth the week before, which shows that 2% decrease. That's your answer to part A. Part B, find the sales 5 weeks after the end of the campaign. So we're just going to plug in 5, and again, simplify with our calculator. So 20,000 times 0.98 to the 5th power gives me $18,078.42. Okay, see if you can try these two on your own. All right, so let's look at number 1. Again, we want to use the formula y equals a times b to the x. If you have a table of values or a set of points, a is your x value equal to 0 or your y-intercept. So we can find that here. My a is 27. So I've got y equals 27. And then to find my b, I need to figure out what I'm multiplying by from one term to the next. Now you can look at any set of consecutive terms. So I could look at 243 and 81, or 9 and 3, or 3 and 1. I think a really easy pair to look at here would be 1 and 1/3. The question is 1 times what gives me 1/3? And the answer is 1/3. That's your b value. Now if you didn't see that immediately, again, you can take any two numbers that are consecutive. So let's say I pick like 9 and 3. And divide them. The later one divided by the earlier one. 3 divided by 9 would also give me 1/3. And then to the x power, and that completes my formula. Let's look at number 2. Suppose that the retail price of an automobile is $30,000 in 2000 and that it increases by 4% a year. Write the exponential equation that models the price t years after the year 2000, and then again use this model to predict something. So we'll get to that in a minute. All right, y equals the initial value of the car, 30,000. Be careful here, you are increasing by 4%, so we're doing 1 plus 0.04. Number bigger than 1 is going to give me exponential growth, and then t years after 2000, and that's your model. Part B, use the model to predict the retail price in 2015. All we have to do is plug in 15 to represent 15 years after 2000. And again, just type in that in the calculator. And we get, again, to the nearest penny here, $54,028.31. All right, so let's look at some models with technology now. This says, during Spain's economic crisis in 2010, the International Monetary Fund released a forecast of Spain's budget deficit as a percent of its gross domestic product, GDP, from 2011 to 2015, and that's shown in the table below. We're going to find an exponential function that models this data, and where x is equal to, let's underline what's important here, what our variables represent, the years after 2010, and y is equal to the percent, the GDP. We want to know if this is increasing or decreasing. We want to graph the model on the same set of axes, and then we're going to do a projection and talk about if that's interpolation or extrapolation. All right, so you need to get your calculator out here, and let's just review where we're putting everything in. So we're going to hit Stat. We're going to go over to not calculate yet, sorry, just go into Edit. I'm ahead of myself. I'm going to clear out all my lists. Here we go. Okay, and let's get our data in there. Again, X is years after 2010. So if we're typing in 2011, it was just 1 year after. 2, 3, 4, and 5. L2s are those percentages. 9, 6.2, 4.9, 3.8, and 3.2. To find the exponential model, we're going to do the same thing we did with our other functions. We're going to hit Stat. We're going to go over to Calculate, and let's just talk about what we've used before. We've used linear regression for lines in the past, quadratic regression for quadratics, cubic and quartic were most recent. If you scroll down, if you look at 0, it is exponential regression. So make a note to yourself, 0 in your calculator, EXPREG is what we're using for our exponential model. So we're going to hit Enter. It's going to look similar to what we've seen before. I'm also going to store this like I've done in the past. So to store that in my y equals for a graph later, we're going to hit vars, y vars, function, and then y1, or any other y, doesn't matter. And then let's calculate it. And there is my equation. All right, so let's fill it in. Let's say we needed to round to, I don't know, 2 decimal places. Y equals 10.90 is my A. My B is 0.77, and then to the x power, and that would be our model. Also notice your R value here. That might help us later answer a question like number 2. Is this model increasing or decreasing? Your correlation coefficient is negative, which is saying that your data has a negative trend. So we can say that it's decreasing. If you didn't notice that with the R value, you could also look at that B value, the growth rate inside the parentheses there. If you have a number bigger than 1, it's growing, but if you have a number Okay, if you didn't see that with the R value, what you could do is you could also look at the growth rate. The growth rate's that number inside the parentheses. If you have a number bigger than 1, you know that it's growing or increasing. If you have a number less than 1, you know that it's exponential decay or decreasing. So we can say either way that this is a decreasing function. Okay, next we're going to look at the graph, which we've already kind of got it ready to go. If we go to your y equals, we stored it in there. I'm going to turn my plot 1 on. Plot 2 I don't need from earlier. And then again, make sure you hit zoom 9 every time. And then you can see there is the model graphed with our set of data. Shrink that down for you a little bit. Oop. There we go. Okay. All right, so that's our number 3 completed. We've got our model. We know it's decreasing. We've graphed it. Finally, number 4, what did the model project would be Spain's budget deficit as a % of its gross domestic product in 2016? Okay, so to figure that out, we can actually use our calculator if you want. We can calculate a value on this, but we do need to change our window slightly because 2016 is going to be a little further out than what we have right now. So I'm going to make my X max instead of 5 point something, let's make it like 7, or you can make it anything bigger than that, 10. We just need to make sure it'll get past 2016, which is represented with an X value of 6. So now if I see graph, or if I hit graph, I can see that that picture goes a little bit further out. I want to calculate a value. So to do that, we're going to hit second, trace, value, number 1, and you're just going to choose the X value of 6, which represents the year 2016. Hit enter, and the calculator tells us it's about 2.35 is the percentage. And last part of that question, is this interpolation or extrapolation? The answer is it's extrapolation because 2016 was beyond the set of data that we were given. Remember, if it's interpolation, that would be a value that's within the data that you already know. So maybe if we had jumped from 2012 to 2014 and they were asking about 2013, something in between values that we have. But if it's outside of the range of numbers that you're given to begin with, that's extrapolation. Okay, and again, if you didn't want to use your calculator for that value part, you could just plug 6 into this equation and simplify. Just be careful, don't round to too many decimal places. If you were going to evaluate with the equation, you might want to give it like 3 or 4 decimal places to make sure you get an accurate number when you evaluate. Okay, let's try another one. It says the following table shows the U.S. average annual wage in thousands of dollars for selected years from 1980 to 2050 projected. Find an exponential function that models this data where this time x is going to be equal to years after 1980 and y is the average annual wage. We're going to graph it, we're going to make a prediction, and then we're going to make another prediction as well. All right, so you're going to need to take a minute. I'm going to pause the video here in a second. We're going to type all this data in. I won't make you suffer through watching me do it. So again, you're going to hit Stat, Enter, go up to your lists, clear them out. Okay, and our X's represent years after 1980. So 1980 would be 0. 1990 would be 10. Okay, the video is going to pause. Go ahead and get the rest of your data in there. Okay, I've got all of my data in there. So let's go ahead and find our model now. Stat, calculate. You're going to go to 0 exponential regression. Don't forget to store that equation. Vars, y vars, function. I'll again put it in y1. And there is our, bring it over here. There it goes. Model. Let's say I round this one to 3 decimal places. That would look like y equals 11.970, and then my b would be 1.047 to the x power. Let's look at the graph of it. We're going to go to y equals. My plot is already on. My equation's already in there. We just need to hit zoom 9. And then you can see there is my data. Okay, I have all my data in there. Let's go ahead and calculate the equation. We're going to hit Stat, Calculate. You can scroll down or just hit 0 for exponential regression. Let's store our equation for later. We're going to hit vars, y vars, function, y1, and calculate. All right, so we'll drag that over. While we're in the calculator here, let's go ahead and look at the picture. We're going to go to y equals. My equation is already stored. My plot is already on. I'm just going to hit zoom 9, and there's a really nice picture showing this data. So if you were asked at this point if this represents exponential growth or decay or is increasing or decreasing, you could use either the model itself or you can use the picture. The picture is probably the easiest way to tell that this is exponential growth. If you wrote this equation out, let's do that real quick. I'm going to round to 3 decimal places. It would be 13.410 if I round to 3. My b is 1.040 to the x power. But that growth rate, again, bigger than 1, so that tells me that it's exponential growth. All right, let's look at C. What does the model predict will be the wage in 2040? Okay, so 2040 is already in the table, so let's look at it in the calculator. Again, you can just plug 60 into the equation because it's 60 years after 1980, or In your calculator, you can hit second trace, choose value, and type in 60. And it's telling me 137.2 would be the average annual wage in thousands of dollars. So about $137,200 is what this represents. Is this interpolation or extrapolation? 2040 was within the set of data I was given, so it is interpolation. Last question, when did the model predict that the average wage would be $225,000? So the difference here is that 225 is not an input, it's an output, it's a Y. So you can do a couple of things here. You can either look at your table of values, you can find an intersection. Sometimes the table of values is just as easy to look at. So I'm going to hit second graph. And let me actually change my table settings so they're regular ones like you guys have. Let's try that again. Second graph. There we go. And I'm looking for the first time that we reach 225,000. So if these values represent thousands of dollars, really we're looking for 225 here, which you can scroll or you can play with the table settings if you want. And you can see right in here at 72, 73, that's where it jumps. Year number 72, we're below 225,000, and year number 73, we're above 225,000. So year number 73 is the guy we're looking for. So that means it's 73 years after 1980, or that would be the year 2053. The other way to do this is in y equals, to put in 225 in your y2, and then you can see it's there, and then calculate the intersection, which we've done before. Second, calculate, intersect number 5, and then we just hit enter 3 times. And you can see again, we get 72.75, so approximately again 73 years is what we're looking for there. Okay, you're going to try this one on your own. I'll give you a couple minutes. Use your calculator for this. All right, let's see how you did. So I've got my data entered in L1 and L2. L1 represents the age in years, and then L2 represents the monthly premium or the monthly payment for a 10-year insurance term. Okay, so, and this is non-smoking males we're talking about in this one, so hopefully you read that carefully. All right, let's create the exponential function. Stat, calculate, and we're going to go down to option 0. I'm going to store it, bars, y bars, function, y1, and calculate. Okay, let's drag that down. And then I'm also going to need the graph, so let's do that in the calculator while we're there. Y equals, clear out that other guy I didn't need earlier, plots on, make sure you remember to hit zoom 9. And there is my sketch of the data. Okay, so the function itself is y equals, again, I'll give this 3 decimal places. My a value is 4.039, and my b is 1.095 to the x power, where x represents the age. Let's jump down to part C now. Part C says use your model to determine the premium for a 78-year-old. 78 years old is outside of our data range here, so this is extrapolation. If that is the case, please remember, hopefully you remembered, to change your window a little bit. Okay, and actually this window is set at 79, so you might have been okay if you had forgotten this part. I'm going to set it to like 100, just so I have a bigger set of data for maybe later in part D. Okay. Hit graph, and you're going to see I have a little bit further to the right now I can do some estimations with. I want to calculate 78-year-old, so I'm going to hit second, calculate, value, and the age 78 is what I'm trying to calculate. And you can see there it's about $4,662 approximately. Part D, for approximately what age does this model predict a monthly premium of $10,000? Again, probably the easiest way to see this is to look at the table of values. And I'm way up there now. We want to see the first time we hit a monthly premium of $10,000. Oh, but I need to go the other way. All right, so age 81, we're at 6,000. Let's keep going. I'm looking for the first time I hit 10,000, and it looks like age 87 is the first time that that occurs. Again, to calculate that, if you didn't want to use the table, you could put 10,000 in here. You may have to change the window again. Your y's need to be up to 10,000. Right now my y max is only 5,000, so I'm going to make it like 12,000 just to give myself a little extra space. And I can see that intersection now. As soon as you can see the intersection, you can calculate it. Second, calculate. Number 5, enter, enter, enter. And then again, you can see 86.4. So the first year that you are over $10,000, you would round up to 87 years. Okay.